Howdy. This video is on the most stable configuration of a system and equilibrium constants. And so all systems tend toward a configuration that's most stable, the lowest potential energy. Equilibrium is just about the most stable configuration of a system. Understanding equilibrium is essential for understanding chemistry. The next 4 chapters of Chem 114 are just on equilibrium. Today's concepts can be applied to chemistry, physics, and biology. And so after watching this video, you should be able to identify the similarities and differences between the reaction quotient, Q, and the equilibrium constant, K. You should be able to write down expressions for both the reaction quotient and equilibrium constant for reactions. You should be able to determine Q for a reaction. You should be able to determine how a system will reach equilibrium. And given the relative values of Q and K, you should be able to determine if the forward reaction is faster or the reverse reaction is faster. You should also be able to determine concentrations at equilibrium. So systems tend towards the position of lowest potential energy, the most stable. And so you can imagine you had a boulder in a valley. Eventually, the boulder will end up at the bottom, the position of lowest potential energy. And so you can imagine that we're plotting Gibbs free energy, which is chemical potential energy, versus the reaction quotient, which is used to monitor the reaction. And again, the system will always end up at the lowest energy. And so the reaction quotient is just products of reactants. Coefficients become exponents. The equilibrium constant is also products of reactants. Coefficients become exponents. It looks exactly the same as reaction quotient. The reaction quotient is used to monitor the reaction. The equilibrium constant is used to define the most stable configuration. So equilibrium constants are constants for a specific reaction at a specific temperature. And so again, reaction quotient is used to monitor the reaction. It can be defined at any point. Equilibrium constant is a constant for a specific reaction at a specific temperature, and it just denotes the most stable configuration. It is a bit confusing. They look exactly the same, but again, Q changes as the reaction proceeds. K is a constant for a specific reaction at a specific temperature. Now, both of them are products of reactants. Coefficients become exponents. And so again, if we have a 5 here, it becomes 5 here, 6 here, becomes 6 down there. Also, please remember, pure solids, pure liquids are not listed in reaction quotients or equilibrium constants. Their concentration is treated as 1. So here we have H2O liquid going to H2O gas. We could write products over reactants, but again, because that's an L, that's just treated as 1. And so the equilibrium expression for this reaction is just equal to the concentration of H2O gas. We can look at another reaction. Here we have sodium chloride solid going to sodium ions aqueous plus chloride ions aqueous. And so again, we could try products over reactants. Pure solids, pure liquids do not appear in properly written equilibrium expressions. They're just treated concentration as 1. And so we end up with that the equilibrium constant here is equal to the concentration of sodium ions times the concentration of chloride ions. Now, again, pure solids, pure liquids do not appear. So if it has an S or L after it, it will not appear in a properly written equilibrium expression or reaction quotient. Aqueous means dissolved in water, and so aqueous is not pure liquids. Aqueous always are included in equilibrium expressions. And so equilibrium expressions are important because they enable us to determine what are the concentrations at equilibrium. And so here's a very simple reaction. We have N-butane, which means the 4 carbons are in a row, going to isobutane. So we have 3 carbons in a row, and then a methyl group, another carbon coming off of it. And so it's products of reactants, so isobutane over N-butane, and its equilibrium constant is equal to 2.5. And so the question is, if at equilibrium N-butane's concentration is 1 molar, what is the concentration of isobutane? And so we can take this equation here and we can solve for isobutane. So if we multiply both sides by N-butane, we get isobutane equals 2.5 times N-butane. N-butane is given a concentration of 1, and so that means isobutane's concentration would be 2.5. If we look at another example, say N-butane's concentration is 2, and so then isobutane would have a concentration of 5. And so again, equilibrium expressions are important. They enable us to determine what are the concentrations at equilibrium. And so for this reaction, our K is greater than 1, which means that we're going to have mostly products at equilibrium. And so no matter what the initial concentrations are, the concentrations at equilibrium will be consistent with the equilibrium expression. And so that means, again, no matter where you start on this line, you'll always end up at the minimum. And so if the concentration of isobutane is 5 and the concentration of N-butane is 1, does that mean Q is greater than K, less than K, or equal to K? So K, again, is a constant for a specific reaction at a specific temperature, does not change. Q does change as the reaction proceeds. And so Q would be isobutane over N-butane, and so that would be 5 over 1. So Q is equal to 5. So the system is not at equilibrium, and Q is greater than K. So how will the system reach equilibrium? Well, that means you got more isobutane than at equilibrium, and so isobutane will form N-butane until you reach equilibrium. So remember, if Q is greater than K, it means you're over here, and so products will convert to reactants until you get to equilibrium. And remember, it goes to the left by the reverse reaction being faster than the forward reaction. If we were on this side, so Q is less than K, the forward reaction would be faster than the reverse reaction. At equilibrium, the rates of the forward reaction equal the rate of the reverse reaction. And so we can actually calculate what the concentration would be at equilibrium. So initially, we're at 1 and 5. At equilibrium, would be 1.7 and 4.3. So if we plug in these numbers to our equilibrium expression, we do get an equilibrium constant of 2.5.
Butane and isobutane can interconvert to reach a dynamic equilibrium. The graph shows the equilibrium line. If we add butane to the system, the equilibrium is disturbed, and the butane reacts to form isobutane until the equilibrium is reestablished.
And so it's a nice simple reaction. You have one N-butane going to isobutane. And again, so if you plot isobutane versus N-butane, you can get a straight line. And so if you start at equilibrium and then there's a disturbance, so it's no longer equilibrium, the system will try to get back to equilibrium. So if we have 1 mole of Y4 and 1 mole of Y2, and they're placed in a closed 1 liter container, what happens? Is more Y4 formed or more Y2? And so this is our reaction, Y4 going to 2Y2. This is our equilibrium constant. And so if we want to know what happens, we have to figure out what is the relationship between Q and K. And so Q is going to be equal to Y2 squared, products over reactants, over Y4, coefficients become exponents. Now we're told that we have 1 mole per liter, which is a molarity of 1 over molarity of 1. And so our Q is given as 1, and our K is 0.1. And so that means that Q is greater than K. And so that means we have more products than we should at equilibrium. And so for the system to reach equilibrium, products will convert to reactants. And so again, if we want to know what's going to happen, we have to figure out relationship between Q and K. We found out Q is greater than K, so it puts us to the right. And so products will form reactants until we get to equilibrium. And the way that works is that the reverse reaction will be faster than the forward reaction until we reach equilibrium. So if 0.1 mole of Y4 and 0.1 mole Y2 are placed in a closed 1 liter container, what happens? Is more Y4 formed or more Y2 formed? And so again, if we want to know what's going to happen, we have to look at the relationship between Q and K. And so we can plug in the concentrations for Q. And so Y2 is 0.1, Y4 is 0.1, 0.1 squared divided by 0.1 gives us 0.1. And so in this case, Q equals K. The system is at equilibrium, and so there will not be a change in the concentrations. And the rate of the forward reaction will equal the rate of the reverse reaction. And so again, please remember, if you want to know what's going to happen, you have to know the relationship between Q and K. If Q is greater than K, products will form reactants. If Q is less than K, reactants will form products. If Q equals K, the system is at equilibrium. Now Q, with that little 0 there, means standard Gibbs energy. And so that's the change in Gibbs energy products minus reactants. And so that's a constant for a specific reaction at a specific temperature. Delta G, non-standard, is actually the slope of this line. Now, one thing that's very important to notice is that the slope of the line is actually 0 at the minimum, right? And so at the minimum, delta G is 0. Delta G is like Q, it changes. Delta G naught is a constant for a specific reaction at a specific temperature. Now, if we look a little more closely at this reaction, you have delta G non-standard equals delta G standard plus RT. So R is the gas constant, T is temperature in Kelvin, natural log Q, where Q is the reaction quotient. And so delta G equals delta G standard plus RT natural log Q. Also, please remember, because Gibbs energy is a state function, we can do products minus reactants. And so we can actually do products minus reactants under standard conditions. And so this is if we want delta G naught for a reaction. And we can also do delta G for non-standard conditions. And so we'd have non-standard delta G, non-standard delta G. And so if we're looking at as the reaction proceeds, we'd be doing non-standard delta G. And so if there's a difference in the Gibbs free energy, which is again chemical potential energy between products and reactants, then there will be a net change in the concentration. And so if delta G is equal to 0, it's at equilibrium. If delta G is not equal to 0, again, it's the slope. So if delta G is positive, that means the products have higher Gibbs energy than the reactants. And so that means the slope would be positive, and it tells you the direction of the change. And so at equilibrium, delta G equals 0, because again, the slope is going to be 0. And Q equals K. So we can take this equation and we put 0 for delta G and K for Q, and we get this. Now, if we subtract RT natural log K from both sides, we get delta G naught equals minus RT natural log K. And so this is kind of cool. This means that given K, the Eckham constant, we can calculate delta G naught. Given delta G naught, we can actually calculate K. Now again, please remember both delta G naught and K are constants for a specific reaction at a specific temperature. And so if we start this equation, divide RT from both sides, and then take everything to the power of E, we get K is equal to minus delta G over RT. And so this, where we have EXP of minus delta G over RT, is the same as E to the power of minus delta G over RT. And so given K, we can calculate delta G naught. Given delta G naught, we can calculate K. And so delta G naught and K are constants for a specific reaction at a specific temperature. Delta G, non-standard, and Q change as the reaction proceeds. And if we go back to our graph, it's kind of cool. Given delta G naught, which is the distance between products and reactants, we can actually calculate K, which is the distance from only reactants to that minimum. Kind of cool. If delta G naught is greater than 0, that means the products have higher potential energy than the reactants. That means K is less than 1, so we'll have mostly reactants at equilibrium. Remember, this would also correspond to a non-spontaneous process. If delta G naught is negative, so the products are lower in energy, more stable than the reactants, then K will be greater than 1, means this would be a product favor reaction. We'll have more products at equilibrium than reactants, and this would correspond to a spontaneous process. Remember, if delta G naught is negative, that means delta S of universe would be positive. So when delta G naught is less than 0, K is greater than 1. When delta G naught is greater than 0, K is less than 1. Positive delta G naught is reactant favored. we'll have mostly reactants at equilibrium. Negative delta G naught is product favored. We'll have mostly products at equilibrium. And so we found another way of calculating delta G naught. We can do the products minus reactants thing because Gibbs free energy is a state function. We can use my favorite equation, delta G equals delta H minus T delta S, only for a process. We can take that one equation and solve for delta G naught, and we get delta G minus RT natural log Q. And finally, we see that delta G naught equals minus RT natural log K. And so what is the Ekman constant for the following reaction given a delta G naught? And so we saw K equals e to the power of minus delta G over RT. Now be careful, your gas constant's often in joules per mole Kelvin. Your Gibbs energy is kilojoules per mole Kelvin. You have to make sure that you change the unit of 1 so that the units cancel. And so I changed my delta G to joules per mole. And so that moves the decimal over 3. So that gives me 32,910 joules per mole. And our gas constant is 8.3145 joules per mole Kelvin. Temperature is 298 Kelvin, which is 25 degrees Celsius. And so per mole cancels per mole, joules cancels joules, Kelvin cancels Kelvin. The exponent always has to be unitless. And so we get minus delta G over RT as having a value of 13.27. And then if we plug that into our exponent, so we have e to 13.27. Notice that this negative canceled with that negative, so this is a positive number, and that gives us a K of 5.8 times 10 to the 5th. And again, negative delta G means the products are more stable, means your K should be greater than 1, and that's what we got. And so we found our K given our delta G. And so when delta G is less than 0, K is greater than 1, corresponds to products being more stable. If delta G was negative, that means that's what we just saw. K is greater than 1, so that's product favored. If delta G was positive, K would be less than 1, and that would be reactant favored. A system is at equilibrium when it's at a position of lowest chemical potential energy, when it's at the minimum here. A mixture has higher entropy, hence the Ekman constant is going to be a mixture of products and reactants typically. So you'll be somewhere in the middle of those two extremes. And again, delta G not positive corresponds to non-spontaneous, K less than 1 reactant favored. So all 4 of those go together. If delta G naught is less than 0, that corresponds to a spontaneous process, K greater than 1, and product favor, meaning you have mostly products at equilibrium. So true or false, if we make a reaction go faster, we can increase the amount of products at equilibrium. And so that would be false. The Ekman position is determined by the most stable position, the minimum free energy, not the speed of reaction. And so again, we can tell what the final position of the reaction is. We can't tell how fast it will get there. True or false, the bigger delta G naught, the bigger K, and that would be false. The more negative delta G naught, the larger K. Again, delta G naught equals minus RT natural log K. True or false, if one starts with higher concentration of reactant, the Ekman constant will be higher. And so that's false. Remember, the Ekman constant is a constant for a specific reaction at a specific temperature. It is independent of initial concentrations. And so you tell me the reaction and the delta G values, I can tell you the equilibrium constant. And so it does not matter on the concentrations. True or false, the reaction free energy at equilibrium is 0. And so that's true. So that's the non-standard Gibbs free energy. It's a little confusing. You have non-standard Gibbs free energy and standard Gibbs free energy. The non-standard Gibbs free energy is the slope of this line. And so at equilibrium, it's equal to 0. The standard Gibbs free energy is a constant for a specific reaction at a specific temperature. And so it's just products minus reactants, does not change. Constant for a specific reaction at a specific temperature. True or false, the standard reaction free energy is at equilibrium 0. And so again, This is the standard reaction-free energy. Does not change. It's a constant for a specific reaction at a specific temperature. Delta G non-standard changes as the reaction proceeds. True or false, all reactions stop once equilibrium is reached. And so it's false. Remember, equilibrium is dynamic. And so it's just at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. True or false, in an equilibrium reaction, the reverse reaction will begin as soon as A products are formed. And so that would be true. And so again, this is a simple reaction. We have A going to B. Initially, we start with all A. And so some of the A converts to B. And as soon as that happens, we have that reverse reaction occurring. And so as the reaction proceeds in this case, the forward reaction rate gets slower because you're consuming A. The reverse reaction rate gets faster because you're producing B. And then at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. And so delta G naught and K, they're constants for a specific reaction at a specific temperature. If you can determine K if you know delta G naught, you can determine delta G naught if you know K. Delta G, non-standard, and Q change as the reaction proceeds. So please remember delta G and Q change as the reaction proceeds. Delta G naught and K constants for a specific reaction at a specific temperature. I hope that helps.